In section 5 now of Unit 4, we're going to look at probability a little bit more and events involving the word not and or. So we'll look at properties of probability, events involving not, and events involving or. And as I look in your booklet, this is present. So again, a little more background on probability, and take any additional notes, but let's see if you can understand it. So E, we said, was the event from a sample space. That is, E is a subset. Now again, if we tie this into our Venn diagram, where our sample space is the universe, E is in a sense a subset. And remember, we spoke of E complement. We'll be using that as we move on. Again, this is just a review as we think of things in the earlier part of this chapter and then for our final exam. So we said that the probability of something generally is going to be greater or equal to 0, or less than or equal to 1. Now, what does this mean? Well, we see it in part 2 here, where we say, suppose there is no possibility of an event occurring, then the probability of that is the empty set, or 0. How about for number 3, the probability of our subset is always going to occur? Then we say the probability is going to be 1. Now often, as we mentioned, it's going to be between 0 and less than 1 if there is a chance. Otherwise, here there's no chance that the event will occur. That would be 0. And that it's always going to occur, its probability would be 1. So, background as we move on. Now, one of the gaming things, and you may have recalled playing with dice before, a single member of a pair of dice is a die. And it's a 6-sided figure, and I've added it here. Here there's a 1 on one side, there's a 2 on another, a 3, a 4, a 5, and a 6. So 6 sides and a number on each side. So in our example 1, you're going to write this up as a PowerPoint example. When a single fair die is rolled, find the probability of each event. In letter A, that a number 3, this side would come up. Well, there's 6 sides, so it would be 1 out of 6. Letter B, a number other than 3 is rolled. Well, there's 5 other sides with 5 other numbers, so a number other than 3 would be 5 out of 6. That a number 7 would be rolled. Well, there are no 7. A number 7 on this is only up to 6, so this would be an empty set, and the probability of that would be 0. How about for letter D, a number less than 7 is rolled? Well, there are the 6, so the number 7, this will be 1 And remember, in a sense, that indicates 6 out of 6, which is 1, and this, as we said, was the whole. And looking at what the book offers here, these are our calculations. And again, you want the examples and the answers and an understanding of what's going on here. Events involving not. Now, the table on the next slide shows the correspondences that are the basis for the probability rules developed in this section. For example, the probability of an event not happening involves the complement that we spoke of earlier and subtraction, where we take away from the universe those elements in our set. We subtract that, in a sense, our set, and that gives us the complement. We'll see it in action. Now, this next chart is also in your booklet. So again, let's just follow it up and review. So we've talked about set theory, we've talked about symbolic logic, and again, we are familiar with arithmetic. So when we think of the complement, and once again, the Venn diagram, this is our sample space. Let me put E in there. Our sample space would be here. This is E. And then E complement would be what is in the sample space, but not included in the E, the items we are looking for. So that little sign complement, or we can use the word prime for that symbol. Now in logic, what is not E is the complement. So again, not that rectangle or square, it would be that wavy line. That's the symbol in logic. And then here, to get to what it would be, we would have to subtract the value of E from the sample space to get to the complement. Now, in set theory, we spoke of the union symbol. The key word was OR, and it was the V, or the inverted caret. And here we're adding everything up. Everything is included. In intersection, this inverted U, and the word and the caret, and this indicates multiplication. Now, some other words you might recall, we talked about union as being disjunction, intersection as being the conjunction, where things intersect. All right, so some review. Let's go on. Now, the probability of the complement, we've been building up toward this. So P, the probability of not E, remember, not E is the complement of E, is equal to your sample space, which is S, minus taking away what is in E. Now we also have another way of looking at this. So if we have E and the complement, that adds up to 1, the whole. Now if we use a little algebra here, we can take this, move it to the other side. On the other side it just changes its sign, and we get this. Okay? And that is, in a sense, what we have here. Let's go on. So, for example 3 in our PowerPoint series, the complement. So, if we have drawn a single card from a standard 52 card deck, what is the probability that it will not be an ace? Something to think about. So we have a 52 card deck. And that's the whole. That's 1. Now, one way of looking at it is we can subtract from that 52 card deck an ace. Now, how many aces are there in the deck? Well, we said there were 4. So now, when we do the subtraction, remember, this is what we're looking for, but in a sense, we're looking for the complement here, what would be left. So if we subtract getting an ace from the whole deck, we get the complement, which is 48 52s. And I like the idea that I've put 52 over 52 for the 1. That's the whole deck of cards. We subtract the 4 52nds. This gives us 48 52nds. And that reduces to 12 over 13. You always want to reduce it, simplify to lowest terms. All right, now we're going to look at events that involved OR. The probability of one event or another should involve the union and, in a sense, addition of things. So let's look at an example. Now, another thing we want to reflect on before we go on is what we call exclusive events. Now, a Venn diagram might help us on this. And again, as a review. Now, if this is set A and this is set B, would the events in set A be distinct from the events in set B as we show it, illustrated by this Venn diagram? And the answer would be yes. And this would show that items in A and items in B are mutually exclusive. Now, how about items here? We have set A, and then we're doing set B. Now, this indicates intersection. So, would the items in A be mutually exclusive from the items in B? And the answer is no, because they are items that are shared. Now, one of the other things I would like to mention is they're going to ask you to comment on things like this. Is putting on a shirt and putting on a sweater, are they mutually exclusive? And the answer is no, because you put one thing on top of the other. So they're kind of tied up together. Now, how about putting on a shirt and putting on shoes? Ah, that would be mutually exclusive. One thing doesn't have to do with the other. They don't go on the same part of the body. And here is the definition. Mutually exclusive events cannot occur simultaneously. And you might say, well, putting on a shirt, you do that, then you put on a sweater, but you could actually combine them and have the shirt. I mean, that would be a kind of a twist of things, but hopefully that's a good example for you. All right, let's go on. So we now have a rule, and let's see, are these in your booklet? Yes. A little later on in your booklet you'll find this, so you want to be sure you understand what this rule refers to. Now, if A and B are two events, if they are not mutually exclusive, in order not to count something twice, you have to subtract those that intersect. That's what this one is showing. If they're not mutually exclusive, you have to subtract those that are found in both, so you only count them once. And we'll illustrate this shortly. Now, if they are mutually exclusive, then the probability of them is just the sum of the two events. Here, it'd be the sum of the two events, but subtracting out those that are found in both, so they're not counted twice. Let's go on to an example. All right, this is example 4, probability involving OR. When a single card is drawn from a standard 52-card deck, what is the probability that it will be a king or a diamond? Well, let's do the diamond first. How many diamond cards are in a deck? And it's 13 out of 52. Now, how many kings are in a deck? Because this is an OR. And the answer is 4. And you might think the answer is just the sum of these. But wait a minute. One of these diamonds here was a king. So in order to make this a proper probability, you have to subtract that one diamond that was counted here already as a king. And that would be out of 52. So then we subtract the 1 from the 4, get 3, and we get then 16 out of 52. And you can take a 4 out of each one of these. So this would be 4 out of 13 would be your final answer. And there they're showing us the protocol for doing it. Subtracting the 1 diamond king from this, and they get our answer. All right. Here we have, for example, 5, and its probability involving OR. If a single die is rolled, what is the probability of getting a 2 or an odd number? Well, to get a 2, we said, was 1 out of 6. And to get an odd number, that would be a 1, a 3, or a 5. And there are 3 there, so this would be 3 out of 6, which would give us 4 out of 6, which reduces to 2 out of 3. Now notice, because 2 is even, these are mutually exclusive. They can't happen at the same time. And here is the solution. We're now moving into the examples in your booklet from our textbook. And as you do these, you want to be sure you show the work to get the answers and that you understand the mastery of getting the answers, so as you do your homework and then later your tests, you are prepared. So let's just do some of these as we go along. In fact, these we've done in the PowerPoint, so let's just move through this quickly and you can answer them here as we go on. And it's the same answers as we had before. Take a moment, put these by the examples. Now we've had this chart, we've gone through these lessons, we've seen this Venn diagram showing you the sample space E and E complement and the formula to get it. Alright, finding the complement. And again, this is one we did in the PowerPoint slides. So take a moment, read it, and here is the answer. So this is straight just using the complement. Now remember, this 1 is 52 over 52. Now, here, again, we didn't do section 1 of this unit, where if 5 fair coins are tossed, find the probability of attaining at least 2 heads. Now, again, you'd have to work out all of these, and looking at all of the lists, there are 2 to the 5th power, or 32 possible outcomes. Now, once you had figured that out, you would count how many have at least 2 heads. Well, the way you would do this is count those that don't have 2 heads. So here, these are all tails. Here, there's only 1 head. 1 head, 1 head, 1 head, 1 head. So there's 1, 2, 3, 4, 5, 6. So in showing the work of this, and again, you don't have this chart to illustrate all of these, this is going to be 32 out of 32. You're going to subtract the complement of this. These would not have at least 2 heads, so that would be 6 out of 32. Subtracting that from the 1, the whole, gives you 26 out of 32, reduced to 13 out of 16. Now, I wouldn't ask for something like this on a test where you wouldn't have the information that you would need to figure it out. Going on. Example 4. Now, selecting from a set of numbers, and we've done things like this before. Here our universe, our sample space is 1 through 10. Find the probability that the number would be odd or a multiple of 4. Well, odd would be 1, 3, 5, 7, 9, and that would be 5 out of 10. And how about multiples of 4? That would be the 4 and the 8. So there would be 2 of those. So our results, we're just adding them because these are mutually exclusive events, would be 7 out of 10. Now, for part B, this gets a little tricky. So I'm going to clear this up here because I don't want those marked right now. I need the odds. So, looking at this, that they're odd, 1, 2, 3, 4, 5, that's the same still. But now, multiples of 3. So as we do our multiples of 3, and I'll change color, we have this one, we have this one, and we have this one that are multiples of 3. So we would add 3 out of 10. But wait a minute, we've already used the 3 and the 9 because of their odd nature. So to make this proper, we have to subtract the 2 that we've already counted in the 5 here. So this would make this a 1, and our answer then properly is 6 out of 10, which reduces to 3 out of 5. So again, they're giving us rather easy ones, and this would be the level of difficulty we'd have on our test. We're not going to have super hard ones that you might encounter 1 or 2 of those in your homework, but let that be a challenge. And there we see it. And they're showing us using the Venn diagram. Here they were mutually exclusive. Here they were not mutually exclusive. And pause to study if needed. Alright, finding the probability of an event involving an OR now. If a single card is drawn from a standard 52-card deck, what is the probability that it would be a spade or a red card? Well, spades are black. And there are 13 of those in a deck. Red cards are half of the deck, so that would be 26 out of 52. Now, are these mutually exclusive? And the answer is yes. So it would just be the sum of this, which would be 39 out of 52. That reduces, take a 13 out of each one, 3 out of 4. So again, this would be at the level of difficulty we could ask on a test. And there we see the work. Now, of course, all these have been in your textbook as well. Now, for this one, again, they're treating union of several components. Now, we didn't have one like this in our PowerPoint slides, so we're going to look at the chart and the table they give us here. So there is Table 5 from our text, and these are the time and the probability that you would spend studying. And this is just made up to give you an example. Now we want to mention that in this probability column, if you added everything up, this would add up to the whole 1.0. And this would be your time spent. So, pause, take a look at this. I have this table, I have this example in your booklet, but I don't have the solutions. So on this, you're really going to have to pause and look at it carefully to pick out the answers. Now, if I give a quiz question on this, what I'm going to say is, in example, I've cut that off a little bit, example 6 in your booklet, what was the probability that it was fewer than 3 hours? Well, that would be 15% or 0.15. And it shows you how the answer was arrived at. And then for part B, more than 2 hours. That would be 0.85. More than 1, but no more than 5. That would be 0.8. And here they're showing, using in a sense the complement. Read this through. I'm not going to read it all through with you. That would just extend the take time. But notice that the answer here, if you can't read it, it's 0.75 for D. Now, if you have one like this on your homework, you're going to have to look carefully at the chart and know the protocol to solve it. Where, depending upon what is in, let's say, A, fewer than 3 hours, well, that would be 1 hour and 2 hours. It would just be adding these two together. And look through this and give it a study. Now, in example 7, find the probability that a single card drawn from a standard 52-card deck will be a diamond or a face card. Now remember, there are 13 diamonds out of 52 and 12 face cards out of 52, as we see here. But 3 of those face cards would be diamonds that we're already including in the 13 here, so they would have to be subtracted. So you end up then with 22 over 52, which reduces to this. Again, for example 7, be sure you're showing the work, because part of the work may be a quiz question, and then what the answer is. Now, here, Emily is going to enroll in a course. 8 of the courses are recreational, 9 are interesting, 3 are both. So are all of these courses mutually exclusive? And the answer is no, because 3 of them are in both. And Emily chooses at least one of these 2 attributes. So we're going 8 out of 20 plus 9 out of 20, but we're subtracting the 3 that are in both. So this gives us then 14 out of 20, which reduces to 7 out of 10. Again, read this. You may have one like this in your homework. Here they're showing you the protocol for solving it. And that winds up our lesson. We've done enough, so we'll pass this up.